Okay, in this lecture I want to go over the first real extension of our language, which is going to be adding functions. So we're going to want to figure out how do we define functions and also how do we call functions in Lattice. We're not going to cover the abstract syntax or the semantics right now. We're just going to do the concrete stuff to sort of figure out what do we want it to do. So what we're going to want for our concrete sort of style is we want something that'll look like this, right? Let x equal 15 in let foo equal a function of z, and then we'll have braces that close in foo of x. Right, if we wanted to translate this into Scala, we'd have something like val of x is equal to 15. Val foo is equal to this anonymous function. And then we would just call foo of x. Right. So one of the first things to notice here is that in Lattice, all functions are anonymous. They're just defined like this, right? We have function with parameter and the stuff that it does. The fact that we have let bindings lets us give us a name to this anonymous function, which is helpful, right? Because we don't want to have to write down the full function definition every time we use a function. We prefer to be able to refer to it by a name, right? But all of the ways that we just define them are anonymous, right? We basically do this, and then we assign it to, for instance, over in the Scala version, we would be assigning it to a val. You can see that the syntax is almost the same, right? We just don't write function here because as advanced Scala programmers, we already know that this refers to an anonymous function, right? This is the parameter, this is the body of the function. So yeah, all functions are anonymous, and we can use let bindings to give them a name. Right, so what would, if we didn't have let bindings, right, we could do something like this, right? We could just call function of z plus 100 on 15. Right, this is a perfectly legitimate Lattice program. This is a function call, and this is the function that we're calling, and this is the input that we're going to do it on. But having, being able to give names to it is just useful, right? So we can even compound these, right? Because we could have this, we could get crazy with it. We could do something like function on y is going to be y times 2. And then we'll call this function on 20. And so what's this going to do? Well, it's going to feed 20 into this. That's going to turn it into 40. And then we'll add 100 to it. So we'll get 140 out as our final answer, right? We basically, this gets eaten by this, and then whatever this returns gets eaten by this function. So this is how we could play with Lattice without having to actually give any names, right? We're just doing pure anonymous functions. Now if we, as we notice, this is really similar to Scala's format for anonymous functions, and it's also really close to the original origin of these, which is called the lambda calculus. So the idea is instead of function, we say lambda, and then we'll put the variable in there, so lambda z, and then we put a dot, and we say what it's going to do, z plus 100. And then this one will be lambda of y dot y times 2. And then we can feed it in our input, which will be 20. So this is the exact same function here, but with in the lambda calculus syntax. Lambda calculus, this was invented by Alonzo Church in the 1920s. dealing with just pure mathematics, trying to understand what are functions, how can we talk about functions. So this is was invented before computers, right? And the Lattice programming language that we're designing really is honestly just the lambda calculus. We've added a little bit of what's called syntactic sugar. Right, so we can say lattice is equal to the lambda calculus plus syntactic sugar, right? And this is lambda. Which just says that it's basically lambda calculus, and we've added nicer aspects so that programming it is a little less painful than having to write a whole bunch of these things down. If you had done this course, say, 30 years ago, you might be doing a lot more in sort of a standard lambda calculus style of programming. But, you know, in the current age, we might as well have some of the handy stuff that we're used to in programming languages, like having some typesetting and things like that. For instance, let's turn this into a nice lattice program, right? So what would this look like? Well, we would want to have, right, let's have let bar equal a function. And what is this function going to be? Right, we want it to be this outer one here. So we'll do z, that takes z plus 100 in, right? So we've just defined bar to be this anonymous function in, and then we'll have another let statement, let foo be a function, which takes in a y, and returns bar of y times 2 in foo of 20. Right, so if we sort of unwind this, we see that what do? We take foo, we substitute 20 in for y, that gives us bar of 20 times 2, which is 4, or 40, and then we apply bar, which is a function, so we get 40, and then we get 140 out of it. So this is our nice form of this lambda statement. Right, this is our nice lattice implementation of it. One more thing about our functions here is that functions in lattice only take one parameter. Right, so we saw in our definitions they were all like let foo equal a function of x plus 100, and let's x plus 10, let's say, right? And then in maybe foo of 15. And they only take, we're only allowing a single parameter here. But that actually doesn't limit us in any way. It just forces us to do what's called currying. This is named after mathematician Curry, and it refers to the fact that it's basically equivalent to say if I have a function on two variables, x, y, I can somehow think of that as a function on one variable that gives another function on one variable. Right, so if I get rid of these parentheses, I end up with something that looks like this. We've already seen a little bit of this with the fold semantics, or the fold syntax, where we had the accumulator and the function that we wanted to run. And this is sort of a fundamental aspect of programming languages that have functions as primary values. It lets us be able to talk about a function that can return a function as well as other values like true or false or numbers. So for instance, we could have something like how do we add two numbers using currying? So we could say let add 2, and what is this? It's a function that's going to take in a number x, and what is it going to return? It's going to return a function that takes a number y and returns x plus y in add 2 of, let's say, 2 and 3. Right, so what's going on here? Well, when I call add 2 on 2, right, this is going to replace 2, or it's going to replace x with 2, right? So this part goes right here, and then we'll end up having 2 be bound to x. And what do we have that's in this in the square brackets? Well, that's this function, right, which takes in a parameter which is going to be 3. So 3 is going to be what y is replaced with, and we get 2 plus 3 is equal to 5. Right, so this does seem to do what we want. Again, let's look at this. What this function on x, what does it do? It returns an anonymous function on y, and if we give a value to that anonymous function, then it does whatever's on the inside. And the nice thing about this is that the inside of the scope of here, x, like we can refer to that value here. So we can nest a whole bunch of these in order to get as many parameters as we want, right? It's just that we end up writing it like this. So in sort of a type systems way of looking at this, we could notice that if we had a version that took in 2 parameters, right, like this, so we have x, y. This, what is the type of this program, right? Well, this function. It takes in, let's say, 2 integers, right, a pair of integers, and it returns an integer, right? This arrow is, again, remember, represents a function that takes something of this type and returns something of this type. So if we look at our curried version with x and y, what does this look like? Well, this looks like I have a function that takes an int to an int. Or sorry, it's a function that takes an int. And what does it return? It returns a function that takes an int and returns an int. Right, because again, what does add 2 on 2 actually give us? This is function on y with 2 plus y. Right, this is exactly what this means, right? If we actually sort of think about what's going on here, once we plug the 2 in, we return whatever is in the body of this. What the body of this is a function, so we're returning this function where we've bound 2 to x. And so this is the gist of what currying is. It takes ordered tuples and sort of replaces them with nested sequences of functions.